欢迎登入 IC 部落格，
让部落格阁主谢美芳带您网罗市场情报，链接产业趋势，预见科技未来。请登入 IC 部落格。
欢迎听众朋友再度收听 IC 部落格，我是阁主谢美芳。那么在节目上呢，要和听众朋友在开源这样的一个专业领域呢，和听众朋友在节目当中分享，在邀请我们每年一定会相逢一次的晶心科技资深工程师蔡传资这位优秀的科技人来到节目当中，同时他今天也带来了一位国外的嘉宾，一起来和听众朋友谈这样的一个重要议题。首先节目欢迎的就是我们的蔡传资，传资欢迎。
非常感谢美芳姐的邀请，感谢各位。
接下来呢，还要欢迎一位嘉宾他的身份比较特别呢。AI 时代来临我们有很重要的这个 IC 的设计有一些重要的像 PDK、EDA 这样的一个工具呢，是非常重要的一个设计的一个起源，可以为晶片设计工业呢带来梦幻的一个改革。那这位背景有一点特别，原本呢是在 Google 服务，他新创了一家公司叫做 wafer space。Please welcome Tim Ansell, founder of Wafer Space. He is a true pioneer in open source silicon, making chip design accessible to everyone. Welcome, Tim Ansell. Nice to meet you.
Thank you very much for having me.
传资，你一定会每年设计一个创新的主题来延伸。那今年呢，你把这样的一个开源的一个概念用什么样的一个具体的公司甚至呢，它会带来一个业界重要的一个革新，在我们 AI 时代新来临的时候，带给我们很大的一个改变
在5年之前，那时候没有开放原始码的 PDK 工艺的套件库，然后也没有开放原始码的 EDA 工具。但在 Tim Ansell 他的帮助之下，我们终于能够有一个开放原始码的完整的过程。你可以一个路边的就是大学生或甚至是完全业外的人士可以去做自己的晶片，这件事情是在 Tim Ansell 的这样的努力之下才办得到的。那当时他人在 Google， 那受限于一些大公司，他有他的一些限制。那在5年后，他现在离开了 Google， 创设自己的公司叫 wafer space， 现在是跟大家比较熟悉的另外一间半导体制造公司叫Global Foundries 革新去做合作，让大家可以用开放原始码的方式，在$2000这样子的一个价格底下去做你自己的晶片。那在 AI 时代，当然现在也可以有更多的方式来帮助这样的一个过程。
Tim, why do you want to leave Google? You know, this big company astonished everybody.
To answer that, you kind of have to look a bit at my history.I'm an Australian. I was born in Adelaide, and I'm actually, quite old now. When I was growing up, none of anyone around me was involved in technology in any way. My mum was a social worker, and my dad was an artist and stayed at home. And they didn't even know that you could be a programmer as a job.A thing that really existed in my sphere.And how I kind of got into Google was through the internet and working with open source software projects. Open source software really has enabled me as a person who otherwise had no connections to these industries to get into the industry. And I think that kind of enablement that allowed me to get the so-called dream job at Google is really important. And so for a long time, I have tried to help other people, get access to this type of thing because there are so many people out there who don't have those opportunities. And so a software engineer at heart, but about 6-ish years ago, I started getting involved in semiconductor-related stuff. And I noticed in the semiconductor space, there isn't a lot of those opportunities available. It's a much more traditional pathway where you might have to go to one of the top universities in the world. It's the only real way to get into that industry. And I looked at what happened in the software world, where in the software world, anyone who can get access to the internet and laptop can become a software developer these days. I wanted to see how we could make that possible in silicon. And I know like it's awesome to be here in Taiwan, which, makes some of the most advanced semiconductors in the world. So it's cool to be invited to visit here. And I'd really like to make it possible so that anyone is able to design silicon. Initially, being at Google really helped that pathway because, Google's a big name, as you said, and it opened the doors to allow me to talk to these foundries and convince them to publish the PDK in a manner that is familiar to me as a software engineer. When you're a software engineer, you just start writing software. You don't have to go to university. You don't have to sign an NDA or a legal agreement. You just go on GitHub and, you find something that you're interested in and you get going. And so I wanted to see that happen. And in the silicon world, and the PDK not existing in that ecosystem meant most people didn't even know that how chips are made. And as a software engineer, none of my stuff works without computer chips, right? Computer chips needed to run the software that I developed. And so the fact that this is kind of one of the humanities' crown jewels of things it's done, it's up there with going to space and, DNA sequencing and these massive achievements, yet only a very small number of people have access to it or even know how it works. And it underpins everything about how we do stuff. And so I think everyone should understand it, at least a little bit. I think probably here in Taiwan, given, you're home of TSMC, you're probably ahead of a lot of the rest of the world in understanding how important semiconductors are. A lot of the rest of the world only recently found out how important semiconductors are. But they are fundamental to humanity's, existence these days. And so being able to enable it and drive the cost down to a point where anybody can do it, whether they're in, the home of the semiconductors like Taiwan, or if they're in, say, Africa in a rural village, or, in Australia, Australia doesn't really have much of a semiconductor industry, can access and make chips, I think, just from it being such an important part of life, should be something that is available. And at Google, Google's a big company, and because of that, you can only do certain things, right? And so by being a small company, you have a lot more freedom. And so that's why something like Waferspace works as a small company. I think people are somewhat surprised at how small Waferspace is. We don't have any full-time employees, but in the last year and a half, we have helped probably about 100 designs be created through Waferspace. And I think people who are used to traditional ecosystem might be shocked that amount of designs was able to be made by mostly people who have never done silicon before or had access to this before in such a short period as well.
We heard some keywords such like PDK, EDA, and what is PDK and EDA and why it's so important for semiconductor industry?
I like to think of it as a software engineer. There's 3 parts to making a silicon chip. The first part is the low-level part, the rules needed for the actual manufacturing and design, and that's the PDK, the process design kit. I tend to pair this with also access to actually getting the chip made. And so that's kind of the first thing. The second thing, you need the EDA tools or electronic design automation. These are the things that take what you've described and convert it into something that is actually real and can be manufactured. And that uses the data from the PDK to generate the design. And then the final part, and this is what makes the chip actually do something, is the RTL or the design. And that's often written in languages like Verilog or VHDL. And that's the human readable description of what the chip is supposed to be done. So you need all 3 parts to make a silicon chip. The PDK, if you don't have access to the PDK, it's very hard to do the other 2 parts. And so that's why when I came into the industry back, 5 or 6 years ago, I was very shocked to find that this kind of fundamental low-level part that is needed to any design or manufacturing wasn't available to me and wasn't something that I could access and just find on the internet like I can find all, the low-level details about software development and all that type of thing. As well, there was quite a big investment in improving the EDA tools out of the US, and the DARPA had invested heavily in making the open source EDA tool quality quite a lot better, but they were also struggling with the fact that without a PDK, how do you test that your tools are working correctly? They had some fake ones, but when with chips, you really need to send it out to be manufactured and get the chip back to verify that it really works. You can do lots of simulation, but nothing beats actually having the physical object. And so that's kind of why I've been focused so much on that area. And a PDK by itself isn't that useful unless you can actually work with the foundry to get your chip manufactured. And so I started Waferspace to fill in that part with a global foundries here in Singapore in Asia. There is also an equivalent to Waferspace called Chip Foundry that works with Skywater in the US. And then there's another foundry in Europe called IHP, and they offer a PDK as well. And so there is now an open source PDK that you can go to, and you can look inside and see all the details from pretty much each region of the world. There's one in the US, there's one in Asia, and there's one in Europe. And that's a pretty big change from 6 years ago when there was pretty much none available. And I think what we've seen is that once that data is available, the quality of the tools have improved really rapidly, and the type of designs people are able to do have also increased in complexity, and the type of people who can also do these designs has rapidly changed. We've now seen high schoolers and middle schoolers design whole chips using this open source process because, a high schooler can't sign a legal NDA, right? So they need the PDK to be accessible and open because otherwise they can't do this work. And so the PDK is kind of the fundamental block that you need that the rest of the semiconductor stuff is built on. And even though we're working at, say, 130 nanometers, 180 nanometers, which is kind of from 2000, 1999 to 2001 was when these technologies were brand new. When you're just getting started, you shouldn't be using the most advanced PDK. That's trying to design a skyscraper when you haven't even built a doghouse or a little birdhouse type thing before. And so really I'm focused on that initial step, getting people into this with these older technologies. And these older technologies are much cheaper as well, which makes it accessible to people. I work with another group called Tiny Tapeout. They have made it so cheap that the cost to get your IC manufactured and get a dev board back with it is about the price of a, nice meal at a restaurant for two type thing. It's about $200. And so that is something I don't think the industry has ever seen before, is that, $200, a high schooler can afford to get a chip created. And it turns out there are high schoolers out there that are doing amazing things that previously wasn't thought possible, but it wasn't possible not because the high schoolers weren't smart enough, but because they didn't have access to the three things they needed to build these chips.
就是晶圆厂会提供一种东西叫 PDK， 那就是今天你实际上这些逻辑闸，就是说你今天设计晶片最基础的元件要如何使用你的那些氧化的金属层啊，要怎么去蚀刻出来，这种东西叫 PDK。这东西因为它是事关于就是foundry它最核心的就是它的能耐的极限，比如说它能够跑多快，比如说会不会漏电，那这个其实像你台积电跟三星之间就有竞争关系，所以过去其实晶圆厂是非常非常不愿意去揭露这样子的一个组件的基本元件给一般的人，如果你要拿到它，你就必须是一间要么是 像 Google 这样的大公司，如他之前过去的雇主，或是你可能说是台湾非常顶尖的学校，比如像我是交大，或是像是台大这样子一个非常顶尖的学校，才有办法去跟这些晶圆厂去签 NDA， 就是所谓的不公开的这些法律文件。但在这个之上，你会需要一个软体叫做 EDA Electronic Design Automation， 它可以帮你把你设计晶片所撰写的所谓的硬体描述的逻辑转换成这些基础晶圆厂提供给你的基础元件的一个软体。这东西在过去也是一个，因为它跟很多智慧财产权有非常非常大的关联，它有非常多专利，而且同时像最近美国与中国之间就有贸易战，美国会使用这样子的方式禁止你中国使用，所以这些东西其实都是一个非常兵家之争并不开放的东西。那在 Tim Ansell 过去的5年之间，这些事情因为美国想要重新再去让晶圆制造的部分可以被带回给，如同刚刚他所说，比如说对美国人来讲，可能他根本像高中生，对他来讲他们没有所谓的 TSMC， 没有像 UMC 联电这样子的公司，他们可能第一个就业选择并不会是去晶圆厂。那要如何让一群根本没有办法去签 NDA 的人去拿到刚刚讲的 PDK 跟 EDA 这样子的东西，需要靠就是开放原始码这样子的东西，就是说它这东西你可以完全去网络上点一个连结就可以下载到一个 PDK， 跟点一个连结可以下载到一个软体，这样子就可以去做一个晶片。那如同刚刚Tim Ansell所说，他目前现在有高中生可以花200美金，也就是大概快6万块台币，就可以做一颗自己的晶片出来。这样子才能够启发一个高中生想要去当一个晶圆工程师，当一个 IC 设计师，就是他必须要这样子的一个足够有经济上允许又可以不会被法律所绑住的一个状态下，才有办法带领人进入这个领域。
休息片刻，稍后回到 IC 部落格。欢迎你再度回到 IC 部落格节目上呢，和听众朋友在开源领域呢，和听众朋友分享。Tim, to make 130 nanometers PDK for actual IC manufacturing is such a long and painful journey. What is the belief that supports you to go through this whole journey?
I like to think that software engineers have a little bit of an arrogant streak. They think they can do anything because of how powerful software is. And that gets us in a little bit of trouble, but it also means that we're willing to attempt things that otherwise seem impossible. And when I, started getting into this journey, I had very little knowledge about how hard it was going to be. And so I just started doing it. And I think in some ways that is both a positive and negative about being a software engineer, is that you think kind of, how hard could this be? We've done all these other things that seem impossible. This will just be another thing that does. And then once you get started, you've told people you're going to do it. And so now you actually need to deliver. And that keeps you going forward. The other thing, as I think I mentioned as well earlier, was that this really is one of the most important things to modern life. It enables everything about modern life. So the fact that it's such an important part of, modern life and so little understood, seems to me that there's a lot of things that aren't being done that would make life even better if it was more widely available. And so that belief is what, kept me going when, I was spending late nights working with the lawyers to try and get a contract agreed for when I'm patient. Like, I've been doing open source software since 1994. Back then, nobody knew what open source software was. But today, open source, all the biggest companies in the world use massive amount of open source software. It's fundamental to everything that the internet is built around. Even Microsoft uses a huge amount of open source. But in the Silicon world, that hasn't been much of a thing. And so having to explain concepts of what open source means and, the expectation that the PDK needs to be on GitHub and accessible to anyone. You can't have it so that there's a sign up form and they email it to you. It has to be on GitHub to be usable by software engineers. Was a long process of explaining it to the VP and then explaining it to the SVP again and then explaining it to the CEO that, this is a thing that could be beneficial to your business and enable you to get more customers, because particularly these older technologies are very much looking for new ways to continue to make money because they're 25 years old, and enabling more people to use it means they're going to get more customers in the end. And so that was a hard process, and I was pretty optimistic that when, thanks to my history with open source and seeing what had also happened in the hardware PCB manufacturing industry, I'd seen the change there as well. Thought that we could replicate this in silicon. I'm old enough that the first PCB design I did, the only reason I was able to get it made was because I was in uni. They did it as a favor for the university, right? It wasn't, I couldn't just go to a website and order PCBs or anything like that. My supervisor had to call in a favor with the company to get my PCB made. Today, it's very easy. You can go and get a PCB made in seconds. And so I saw that evolution happened there, and I was like, why can't we do the same thing in silicon? And so seeing that made me think that it would be possible. And, again, a little bit of arrogance and knowing what I was getting myself into was very much the case of okay, now I said I'm going to do this, I need to do this. And so I think what has kept me going, though, is just I was pretty optimistic compared to what people from the silicon industry was telling me to have expectations about. And then the results were absolutely way beyond even my optimistic expectations were here. As an example, when I started the program at Google, we started by offering free silicon tape-outs using the PDK at Skywater. Industry was telling me that you need to, only do one a year, and that you're never going to get 40 designs on this PDK that you're releasing, and you're going to only give them 3 months to do a design. That's not enough time. There's no way you're going to get 40 designs. And then on the first run, we got 40 designs. And we were like, okay, that's great. The second run we did, everybody was telling us, it was just pent-up demand. People had just not had access to it. So you're never going to get 40 designs for the next one because, you've already used up all the people who would do designs. And on the second run, we get 80 submissions. And then out of that, this guy called Matt Venn, who had never done ASIC design before, he'd done a little bit of FPGA work, came up with this idea, the silicon space that he's been given by Google is too big for what he wants to do it. So why doesn't he share it with his friends? And so he built a thing on top of that basically meant that he could divide a chip that on Google's MPW program up to 200 different people. So 200 different people could put a design on a single chip. And everybody who saw that said that was, crazy, you'll never get that to work, all that type of thing. And now Tiny Tapeout has created, I think they're up to about 20 chips, almost all of them being full of designs from every walk of life, from senior designers at people like Nordic and TI, to high schoolers, to even a couple of middle schoolers, to hobbyists, to scientists that are working at CERN, to scientists that are doing agriculture stuff in the middle of Australia. They've even sent one of their chips into space. And this was from a person who previously had no semiconductor experience whatsoever had gone from that to teaching at least 10,000 people to do their first tape out and given them a chip. And like that is way beyond what we expected, right? Like we expected maybe we'll get a couple of hundred, maybe 1,000, and then this one person and his program Tiny Tape Out has dramatically changed how accessible it is. And he went even further. It's like, you don't need to install any tools on your computer. You just go to a web browser and it all integrates with GitHub and runs all the tools on GitHub Actions. And so that is a really like cool example of something nobody thought about would exist. And some person who had a different point of view came in and said, why don't I just divide it by 200? And one of the problems that has existed in this industry is that it's got increasingly more expensive to do things in this industry. Like if you look at how much TSMC has to spend on their new fab, that's like an astronomical amount of money, right? Like the ASML machines being super expensive, like that is a huge amount of money. And so only companies that need 1 million devices can afford to get stuff manufactured anymore, because they need to take that really large number and divide by 1 million people to like get it to a reasonable size number. But if you look at like these older technologies are cheaper, but if you divide, say, the number, so like with wafer space, the way wafer space works is we divide the reticle by, say, about 40, and so the cost of doing the mask run and the creation of the silicon is not cheap. But when you divide that number by 40, it gets down to, you know, the $1,000 range type thing. And so with wafer space, I'm now enabling people to get 1,000 parts back for $2,000. And I'm doing that not as a philanthropist, not as a person who, you know, is losing money. That can be done with wafer space making money, with Global Foundries making money. It's not a loss program because we take a big number and we divide it by a reasonable size number. It's not like rocket science to do this. And we also automate a lot of stuff. As I said, a wafer space doesn't have any full-time employees. I do all the paperwork, and then we have a person who helps with the receiving of designs, but that's mostly automated because as a software engineer, writing software to accept designs is not a thing I'm scared of doing. And especially with like AI now making developing software so much easier, the fact that we can write this software that automates what previously required lots of people to be involved with also drives the cost down and makes it so that we can make this type of service profitable, even though the costs can still be quite high. And it's all based on the idea that we need lots of people to actually want to do this. And what I've seen is that as you reduce the cost, the amount of people who want to do it dramatically increases. Like the thing I kind of think about is like the number of people who can afford a tape out at $200 is like, say, 60% of the world can afford to do a tape out at $200. At $2 million, maybe, you know, only 1% of the world can afford to do a tape out. And so the being so cheap, we have people from everywhere in the world that are now doing tape outs. And by getting people back 1,000 parts, which is what wafer space does, they can actually use it in real products. You know, lots of small businesses only might sell 1,000 of something every year. Previously, their only choice was to use off-the-shelf parts. Now, because it's cheap enough and they're getting back enough parts, they could decide, if needed, to create a custom chip for their product, because they only have to recoup the cost of, you know, the $2,000 or $7,000 of the design rather than having to recoup the cost of $2 million. And so all of a sudden, people who previously thought that, doing an ASIC didn't make financial sense for their business or the product they're making because they're only selling a small number of them, can suddenly go, okay, yes, I could do this, and, it makes my product smaller, more power efficient, or something like that. It really can enable, new things that weren't possible. And so we're seeing lots of people come on board and are like, okay, it's not the most advanced technology, but most things don't need like the most advanced technology to do something interesting. And they're trying lots of new interesting ways to do things. And we're seeing other stories like what Matt Venn did with Tiny Tape Out, of people coming in and doing something a little bit weird, a little bit not like the traditional industry, and having success with that. We've seen an example of a high schooler create a full microcontroller, like an ST or an Arduino level microcontroller entirely himself. He's obviously a very smart high schooler and is now like in one of the top university programs, but he was able to do a tape out in high school because of these programs were cheap enough that he could do that. And he did a full microcontroller that previously we would have said would have required, a couple of engineers to do. And then we also have an example of a embedded engineer who his day job is he works on like the Linux kernel as a developer for drivers and stuff like that. And in his spare time, he created a Linux capable CPU from scratch. And again, it was kind of a case of being a software engineer. He didn't know that creating a Linux capable CPU is supposed to take 20 engineers worth of people to do it. He didn't know that you weren't supposed to use an old technology like this. You need to use a more modern technology, apparently. He didn't know that, it was supposed to be as hard as it was, but he managed to pull it off. He managed to fit a full Linux capable CPU on these older process technologies in much smaller space than I would say most people thought were possible. And one of the other cool things about this is because he's a software engineer, unlike most hardware that you get from industry, it runs the upstream Linux kernel. So unlike a thing from, say, like TI or something, you don't need a board support package. You just go to the normal place you get your kernel and you download it, and it just runs by default. You don't need any of this specialization that a lot of these companies think as required to get their products to make them usable. He was just like, I'm just going to make it work by default. And that's what happens when you have somebody, again, who comes from a different background. He's obviously, a very smart person. I'm not sure I could do what he did, but I'm sure there are other people out there like him who could do it if they just had access, right? And so these are kind of examples of like smart people out there that are at, some of them are still in high school, some of them are retired, some of them are in university, some of them are in total different industries. There's a bunch of people who are like doctors who are like, I want a chip that is different from what the industry provides, but, there's only 10,000 people in the world who would use this chip. So I'm never going to, be able to do a TSMC chip because that's just way too expensive and there's not enough people who would ever buy this. But I can consider doing it with like things like wafer space because it's so much cheaper and they only need a couple of thousand chips to do this. And so it's really increasing the audience. And when you have a large number, dividing it by another large number makes a small number. And that's why this whole thing works, is that basically by making it cheap enough, you've unleashed the number of people who can do this and who can do designs and stuff like this. I'm sure there are plenty of designs on this that an industry professional would look at and go, that's a really bad way of doing it. But like when it's cheap enough, it doesn't also matter, right? Like if I'm spending, $500 million on designing a chip, I want the best chip ever, right? Like, but if I'm only spending $2,000 on it, it doesn't matter if it's not the best. If it fit for what I need it to do, then it's usable, right? Like I don't need it to be the best performance. I just need it to work for what I need it to. and I don't need to spend as much time doing the optimization because I don't have to claw back all that NRE that has been spent on doing the development, right? I can just go, well, it only cost me $2,000. Actually, if I get the chip back and it's unusable, I only spent $2,000. I didn't spend. If I get $500 million chip back and it's unusable, I'm pretty sure somebody's getting fired, right? But $2,000, it's not so bad if it doesn't work. And so that also reduces a lot of the complexity of like what you're doing because the costs are so much lower. The risks and the opportunities are a very different space. And so I don't think like the big guys are going anywhere. We're not even in the same field. But some of these people might find that their chips, become successful in their field and all of a sudden they want 1 million of them. Then they'll start talking to, these other companies to scale up. But it's much easier to justify doing $1 million investment in creating a new chip if you've already sold 1,000 of those chips, right? If you've never sold them before, how do you know that $1 million investment is going to be worth it?
休息片刻，稍后回到 IC 部落格。欢迎你再度回到 IC 部落格。节目上呢，和听众朋友在开源领域呢，和听众朋友分享。
So that's kind of the thing. It's an economic, like I'm a software engineer, but this is really just basic economics type level thing. It's not really rocket science, but it's all enabled by these tools being easily accessible and that type of stuff. If you're a high schooler, as I said, you can't sign an NDA, you can't get a lawyer. And so the moment there's a contract involved, you eliminate that entire class of people. And same with like a lot of other people. Software engineers are notoriously fickle in their tools that they want to use and stuff like that. And so if you try and enforce that you use tool A or tool B or tool C, they're just not going to do it. And so we don't require that. As long as the design they submit to us passes the design rule checks, which means it's manufacturable, we will manufacture it. It doesn't matter if it's a design that is just a pretty artwork. We actually have some artists who are like, well, this is cheap enough now that I can make like little jewelry out of silicon, which might be something cool that people here might enjoy. Silicon such a port as you can get, because silicon chips are also very pretty if you've ever seen them. And so they'll put like little embedded artwork in the silicon. And because it's cheap enough, it's $2-3 a chip, they can make affordable jewelry which has this unique aspect. But you're never going to sell, it's not a mass market product that you're going to sell 100 million, silicon chip earrings or something like that. UC Santa Cruz just submitted, I think, 8 designs from their undergrad course on our run number 2, which was pretty amazing. They originally were targeting somewhere else, but they didn't get the funding they wanted. And so the only way they could do this is to go with wafer space, because wafer space is much better value proposition. If they were trying to go with a different service, it wouldn't fit. There are definitely a lot of other community colleges in the US. We've had a professor from Columbia University, analog chip called Mosbius, he made the chip so he could better teach semiconductors to his students. And, he needs enough chips that he can give them out to his students. And it's a really cool, like, little analog design that is supposed to help you learn about how transistors work. And so it was cheap enough that him as a professor could design to get a chip specifically created for his university course so he could better teach how transistors work, which I think is a pretty cool idea, that you're actually making a silicon chip so you can teach silicon chips better.
就是他本身自己是一个 provider， 他提供$2000这样的一个方案，让你可以做自己的晶片。其实晶圆就像一个松饼一样，上面这块松饼你要摆什么料，其实是可以切割的。所以$2000是给一个固定的大小，在一个圆形晶圆上。那他有一个在西班牙的一位合作人士叫 Matt Van， 那他把这样的一个晶圆切给他的部分，再切给别人。原本你$2000，他切给10个人，一个人就只要付$200。 那拿到的那个面积再变小一点，但是还是可以做足够的使用，比如说可以做一颗可以开作业系统的晶片，或者是说甚至有人无聊拿去做成一个是耳环，这样也可以。200美金对一个人来讲，他今天如果是艺术家，其实晶圆上面，因为它晶圆本身并没有什么神奇的地方，它其实就是一堆电路线。如果今天在适当的编排之下，它甚至可以去，就你肉眼就可以看得到上面有什么样子的花纹，所以就还甚至有艺术家他说就拿去做成一个耳环，做出这样子的使用用途。所以它作为2000美金的一个中盘商，下面还会有零销商帮他去把这样子的空间卖出去，所以这本身其实是一个可获利的模式。那它在真正用途上的教学上，是 UC Santa Cruz， 就是加州大学圣塔克鲁兹分校有相关的大学实验室已经在使用这样子的它的 wafer space 来进行教学，以及所谓的 community college， 美国的讲法叫社区大学，以台湾来讲就有点像过去的3专或5专，或是所谓的4技2专职业学校，叫做哥伦比亚 Columbia 这样一间，就是以台湾来讲就是技术学院，也在使用它的 wafer space 进行类比电路的 mobiles 的教学。所以就是有来自于这种纯粹的分盘出去的客户，也有来自于甚至很特别的是艺术家的这种使用用户，然后有一些是自己本身可能有小批量，比如说他卖200片这种非常非常小的个人自己开他特殊的使用 IC， 比如说音乐或者是图形设计的这种小处理器，过去只能使用既有就是现场你在外面经销商买得到的晶片，但是现在你可以自己去写自己去做，那200美金或2000美金这样子的一个价格的价带，是对于这样子的小型自己开晶片来做设计的人是可以负担的钱。那对他来讲，他就是收一个中间的这样中盘商的手续费，是足够维持他的这样的生意的模式的。所以他并不是一个慈善家，他也没有赚大钱，但是就是一个是足以让他的生意损益两平的一个生意模式。
开源的一个概念哦，它可以透过大家的这个共享之后，再把这些模式哦，也可以在台湾一个核心一个 team 做出发想到全世界各地去，让大家更加的看见台湾的这个能量。那个能量又是什么？我觉得就是一种民主 IC 军强。好，我想知道你的这一系列的做法想法是什么。
很感谢美芳姐在这5年之间也一直就是纵容我们 COSCUP 这样来节目上带来各样的讲者。今年在 COSCUP 我们也邀请到了来自浙江创新的 eCOS Team 的王浩博士，以及来自日本惨重研的 OpenSUSE 这样子的一个组织的 Jim 桑。然后原本都有打算要来贵电台进行采访，但很可惜的，因为白海豚的台风的关系，所以班机有一些状况，最后没有办法成行。但是在这5年当中，我们也包含邀请到 Frank Vater 来自于德国的 IHP， 以及苏黎世邦理工来自于瑞士，以及我自己本身是来自台湾的晶心科技 Andis Technology。美芳姐刚刚就提到，就是是一个民主晶片的概念。我们在这样子的一个大家共享共荣的环境底下，来台湾这块以半导体产业为闻名的土地上面，大家进行技术上的交流，能够带领大家可以得到更多的资讯。那如同刚刚Tim Ansell也有提到说，就是他本身自己是一个 software engineer， 是一个软体的工程师。我们软体工程师在自己的心中都有一些愿景，如同刚刚Tim Ansell说，他在澳洲的一个乡下长大。你如果今天没有网际网路，他是没有办法成为一个软体工程师的，没有办法进入 Google。可是因为软体工程师的进入门槛非常的低，你今天你可以在网络上面上网就可以得到免费的教学，来学习如何写程式，也就成功的造成他可以从一个乡村的孩子长大到成为一个在 Google 工作的工程师。我自己本身也是一个从小就开始写程式的一个小孩子，因为当时我爸爸要工作，那他自己本身在大学因为很有缘分的当时修习过一些电脑的课程，他就在他工作之余的时候带我去他的工作场所，也就给了我一本电脑教学书。我从7岁开始，因为这样子的关系学会写程式。那相对来说，就是软体这样子的一个进入门槛非常的低。那 Tim Ansell 今天带来的这样子一个开放晶片、民主晶片的概念，也就是让我们可以从原本的软体业很容易进入到晶片业。 让原本只能属于台清交成4大4中这一些顶尖学校才有办法能够取得的晶片教学的资源，可以下放到 Tim Ansell 所提的一些 Community College， 在台湾就相当于是台北工专，当然现在改制为科技大学，可能是一些台科大，甚至可能是一些像地方的技术学院，原本这些都没有能力可以跟我们接下来要进行参访的 TSI， 他们没办法进行这样子的合作。因为半导体研究中心它本身资源有限，它只能提供服务给某些教学单位，那有更多教学单位其实在这个大门之外的，就可以靠 Tim Ansell 的 wafer space 来提供这样子的教学。那如同这一次来 COSCUP 的王浩，就是浙江创新，他们也是有在中国提供所谓的一生一心的服务，那就是要让原本完全被排除于他们所谓985工程与211工程这样子一个顶尖大学之外教学的学生，可以获得晶片芯片制作的经验，就是这样子的一个共享共荣的概念，是大家有一个共识要做的方向。
我觉得这样的一个共享的概念，就是开源价值精神很重要的一个延伸。开放的是一个基本的架构，开源提供了一个很好的一个概念跟平台，让大家可以在这里有一个民主的平台去共享 IC 的一个开源这样的一个价值我觉得 Tim 他所得到的价值也分享出去了，我觉得那是一个很重要的一个科技利他性格的人，他一定有碰到困难的时候就是一步一步的走下去，就自然克服了这样困难，然后现在花园开放的这么大嘛，鼓励大家面对这个事情。
The open silicon space is still very new, but it's growing really rapidly. Wafer space is only a really small part of the ecosystem. There's just so much happening. It has people like big companies like Google and Nvidia contributing, down to high schoolers and scientists and people from everywhere around the world.And it's growing and evolving extremely rapidly. And I'd really love to see, more people from the home of the most advanced semiconductors contributing to this ecosystem and helping push it forward, because it's just amazing what happens when we all work together and use the tools that we have.
Okay.
对于 Tim 跟我这样子的软体工程师来讲，就是看到别人能够茁壮是一个算是心中的一种支撑点，更多人可以使用这个工具本身就是一种骄傲。今天你本身是一个匠人，你做出来的工具有人使用，终究是一个支撑的力量，让你继续走下去。
What's really cool about it is that just so much to do and so many cool things happening, and every day a new person appears and shows me something that I'm like,I never know you could do that, or that is way better than I thought it could ever be, by some person I've never met before, something that I've never done before as well. It's so amazing to have collaboration with people who I may never meet in person. I do like coming to these conferences, and so I appreciate the invite. Taiwan, meet some of the people here.
很多根本这辈子没有见过的人，透过网络上连线，透过这样子的方式，他可以得到原本我们并不知道的知识，就本身是一件非常快乐的事情，然后也可以持续带领我们走下去。
It's a big inspiration, really. IC 部落格，那么今天节目非常的谢谢我们的晶心科技资深工程师，认识了他5年每年一会的蔡传资，再次来到节目当中，谢谢传资，谢
谢美芳姐。
Tim, thank you so much.Thank
you for having me.
IC 部落格节目最后呢，阁主就和2位帅哥一起在节目当中和大家 say goodbye.
Goodbye.